I'm very excited today to tell you about some work in progress that I've been doing with Dr. Carol Feldacker, who's in UW Department of Global Health. But first, let me just say PoCSci Keynote. I mean, wow, this is really an honor. In fact, it gave me the opportunity to start preparing this presentation yesterday. It's also an opportunity to reflect on a system that has been under development for about 2.5 years now, share with you some of the unique capabilities, the challenges, the opportunities for improvement, and contrast it with some of the more familiar computer systems that, that this audience knows. And I will also, at points, refer to a second system that's been under development for about 9 months now. So let me first give you the history and the context. We initially deployed our system on December 27th, 2015. Like many of you, we stayed up all night the day it was going to be released. And since then, it's been a continuous process of learning and iteration through the present to just have the system develop further and further as we go. I should emphasize, however, that the preliminary pre-deployment development started approximately 9 months prior, and certainly my collaborator in this work deserves almost all of the credit for that initial pre-deployment period. I should also emphasize that when it goes from pre-deployment to deployment and becomes a system is something that's often controversial, and that I'm going to try to steer clear of in this presentation. So here's some pictures from the initial deployment. You can see our system on the left, and you can see both our exhaustion and excitement. I just think this kind of gives you the starting point for the work I want to present today. So basically I want to give you a system overview, talk about some of the capabilities, the limitations, focus on some of the systems issues, and then I'll have a couple minutes toward the end for related work, future work, and conclusions. So let's dive in with some of the amazing capabilities. I should point out that part of what our system can do is natural language processing. In fact, we believe our system is in many ways on par with a human toddler at this point. And I should emphasize that there really aren't domain-specific heuristics being used. That this system is capable of idiomatic English and precise technical English. And if I can get my demos to work, let me show you an example of each. So first we have the idiomatic English.
You're the cutest.
But maybe those are kind of simple. What about something a little more technical? Live demos are always a bit dangerous. Okay, let's try again. Can you say function types are contravariant in the argument?
Argument.
You'll notice it helps to decompose the problem a bit.
Function types
are contravariant in the argument. NLP is not all. Object recognition is often also a particular strength of the system. In multiple domains, I would add, although it's fairly highly specialized for animals and construction vehicles. We did this, as many fellow researchers do, by starting with a training set that the system became particularly familiar with, and then moving to a test set, including in unusual environments and even while moving. The last amazing capability I want to discuss is autonomous motion. On the left, you sort of see the thing that various large, well-funded, DARPA projects, this is actually from Boston Dynamics, brag about. You see a bipedal thing being able to avoid a simple obstacle. Well, sure, fine, but this is what we can do. This is actually fairly old. We were able to do this almost a year ago. This was actually recorded at 5 a.m. on a Tuesday. Nonetheless, there's some limitations. If you're going to build a... Hold on. There we go. There's some surprising limitations. If you're going to have a system with these capabilities, there are always trade-offs. There's things you can't do. And unlike many more traditional systems, it's not very good at arithmetic. In fact, it often hangs on seemingly simple computations, and even when it can figure something out, like 2 + 2, it seems to be driven entirely by table lookup. I should also emphasize that logic is a struggle. Particularly in the temporal domain. Now, many of you might not be familiar with temporal logic, but using the standard operators, this statement that you see here on the bottom says, for all future, for some proposition P, for all future, if it holds in some future state P, then it holds in the next state P. And this is clearly false, but the system often thinks it's true, and I find myself repeatedly trying to teach it that later does not mean now. So with that, let me move on to some of the system and implementation issues. Many systems these days care a lot about power conservation and being energy efficient. We do quite well in this regard. I would point out that our system is powered entirely wirelessly. It can go hours without a recharge, although if too much time has elapsed, we do notice serious performance degradation. But I used this website to figure out that apparently the system is consuming about 4 million joules a day, which would actually take several hours to provide via a standard laptop charger. Yet we're able to do it far more efficiently. And in fact, we can use a variety of energy sources. In fact, we're told from experts in this sort of system that it's healthy for the system to get energy from a variety of sources, although we've noticed particularly good performance when using macaroni and cheese and graham crackers. There are challenges, of course. We notice a lot of unexpected panic mode events. They can be seem to arrive almost non-deterministically and without much warning. It often will return from sleep mode far too quickly. Even a loud noise or large vibration can cause this to occur. But probably the biggest challenge we face is the converse, which is putting it into sleep mode in a timely fashion. So I tried to create a graph to explain what's going on. And what you can see on the x-axis, I have time to enter sleep mode on the x-axis, and on the y-axis, I have percentage of time that the sleep mode is entered in approximately that amount of time. And the median is not actually too bad. 10 minutes seems fine for a system like this. But the median, as we all know, is misleading. A lot of times system performance is absolutely dominated by the tail effects. And you see the frowny face over to the right. This can often cause the system to perform badly for up to the next 24 hours. So I did mention we've started working on a second system, which is not as advanced as yet, but may one day reach the first system. And I want to give a little bit of perspective on how to approach developing that second system. As we all know, you want to avoid the second system effect of trying to do everything you thought you were going to do with the first system. It turns out by developing the first system at the same time, you largely avoid that temptation. You tend to find efficiencies, you tend to learn from experience, that's true. And we hope, a lot of people would say, well, why have two systems? Isn't one enough? Well, you hope to reach a point where there's synergistic coevolution, and the systems can in fact help maintain each other and grow together. I will say, however, that not all the tenets of software engineering apply. In particular, we do not expect to throw one away. There's far too much related work for me to discuss here. There's billions of systems stretching back millions of years, although we believe that the earliest systems were far more basic in their functionality. So instead, let me focus not just on the work that's been performed here in UW-CSE, but in fact on work that came after ours. So it's been a very hot area recently, and so I just wanted to show you some of the recent systems. I'm aware of at least 8 involving UW-CSE participation in the last 2.5 years, and my deepest apologies if I've forgotten anyone. It also has not been limited to faculty. I don't want to suggest that you particularly need certain credentials or experience to work in this domain. And in this audience, you might be most familiar with the work of Duro and Duro, which actually started exactly about one month after our work. So let me turn to future work. There's a number of near-term challenges that my collaborator and I are focusing on right now. I already mentioned the sleep mode issues, and we're continuing to work on those. Of particular importance to me is trying to get the system to perform autonomous waste disposal. At this point, several times a day, we need the sysops, which are usually myself, to manually intervene and take care of the system. We believe the system should be able to take care of this on its own. A lot of you are familiar with, you know, human-computer interaction research, or HCI. We're mostly focused on HHI, and we think that'll be a challenge that will continue to grow and develop in the upcoming years. But those are just the near-term challenges. This is a long-term project. I want to tell you about some of the broader goals and vision we have. You know, there's a lot we think systems like this can do autonomously. Some of them may seem frivolous, but I think creativity is one of the things that's a hallmark of intelligence. And I think we could maybe do music generation. Even if we can't do that, I think there's other very important things. You know, more in the intelligence space, there's reading comprehension. And there's a lot of focus these days. You hear it all the time, and with, you know, household names like Uber and whatever, with autonomous driving. But, you know, it's one thing to be able to drive eventually one day a 2004 Honda Civic, which I will probably still have in 10 years. But why not a King County Metro bus? Or why not a tractor in unfamiliar environments? And lastly, something that I think would really be a challenge problem that would mean a lot to this community is the goal of program synthesis. So just to conclude some of the takeaways, I've tried to emphasize, although I didn't get too much into the details of how we perform the reinforcement learning, is that it works. And that's not to dismiss the huge role that genetic algorithms play in a lot of this work. There's a number of constraints of building a system this sort. All your algorithms are being tuned online and adapted dynamically. This is a safety critical system, I assure you of that. We always put safety first. And there's surprisingly high maintenance costs, as you can find out from anyone who's ever tried to develop a system of this sort. I would also bring this a little back to the computer science community and tell you that it's well known in planning theory that if you're stuck with online algorithms, you cannot always achieve the rewards of offline algorithms. But I would say that this is, without a doubt, nonetheless the most rewarding thing we have ever done. Thank you. I do have time for a few questions, if anyone has them.
So how do you do debugging?
Oh, debugging is a challenge. We will often query the system to try to figure out internal state, and it's not often able to provide meaningful data back to us. Yes?
I'm curious how your neighbors feel about it. I'm curious if you have downstairs about this bipedal motion demonstration.
Oh, we do have a standalone home, which proves to be really valuable laboratory space. I know not everyone has that opportunity, and then you need to work under those constraints as well. Yes?
So as a systems researcher, I'm wondering about the initial development of the system. How much implementation complexity was required? And
yeah, I thought someone might ask about that.